double whammy about the double-slit experiment and other kind of topics. So first up, it's MohammadJavad Kazemi from the University of Qom. I hope I pronounced that reasonably okay. And he's going to be telling us about can the double-slit experiment distinguish between quantitative interpretation. So you have so about 25 minutes, if that's okay. And yeah, please just take it away. We'll have questions at the end.
Hello and good day, everyone. I'm excited to be here and grateful for the opportunity to speak with you today. The title of my presentation is "Can the double-slit experiment distinguish between quantum interpretations?" This talk is based on our recent publication in communication physics. In fact, I would like to start with arrival time problem, a challenging issue in the foundations of quantum theory. I will discuss how a modified version of the well-known double-slit experiment can be used to test proposed solutions for this problem, which originates from various interpretations of quantum theory. Let's carefully review the experiment. Imagine a single atom initially confined with a box. For example, in the ground state of the box, the experiment starts when we open the box, letting the atom to freely propagate. After some time, we observe the particle on the detection screen. What is important? It lets us exactly define when the experiment begins, which is needed for the accurate study of time of flight. Experimentally, these flights can be realized with magnet-optical trapping and laser cooling technologies. When we repeat this experiment, each atom is not only detected in a random position, but also at a random time. Thanks to the Born rule, the position distribution is well understood. What about the temporal distribution? This question is without a universally accepted answer, which is called the arrival time problem. We can also ask a more general question. What is the position time point probability density on the screen? Note that the time squared is merely the conditional position probability density at a fixed time, not the position time joint probability density. It is important to remark that this distribution is an experimentally observable quantity. Here you can see the observed data for this quantity in a double-slit experiment performed 25 years ago. Problem, the arrival time problem, arises because in quantum theory, time is a parameter, not a self-adjoint operator. Hence, there is no agreed-upon way to compute the temporal probability distribution of events from first principle. I mean, the above order. In fact, as Pauli proved, there is no self-adjoint time operator that satisfies the canonical commutation relation with a Hamiltonian operator bounded from below. But since clock exists and time measurements are routinely performed in quantum experiments, a complete quantum theory should be able to predict the temporal statistic of detection events. In fact, usually experiments are performed in the far field or a scattering regime, where a semi-classical analysis is often sufficient. In this analysis, it is assumed that particles move line classical trajectories, and the arrival time distribution is computed using the quantum momentum distribution. You can see here the derived expression from semi-classical arrival time distribution, in which psi tilde is the wave function in momentum representation. Nevertheless, the semi-classical analysis is an approximation at best. So this is because its underlying assumptions are not generally correct. Firstly, this analysis gives accurate predictions when the detector is in the far field region. Secondly, and more importantly, the assumption of uniform motion is inconsistent with quantum dynamics of probability density, especially in the near field interference phenomenon. This inconsistency can be clearly understood from quantum backflow effect. Backflow effect is a strange quantum mechanical effect that for a particle with momentum pointing to the right, with probability 1, the probability of finding the position of the particle to the right of some reference point may decrease with time. This counterintuitive effect clearly shows that the uniform motion is not consistent with quantum probability propagation, even in free space. In principle, the detector can be positioned in the near field, where the semi-classical approximation breaks down and a deeper analysis would be demanded. However, in the near field regime, arrival times are typically very short, making experimental investigation more challenging. Nevertheless, due to recent progress in the ultra-fast detector technology, it will be soon possible to investigate the near field regime. To address arrival time problem, various attempts have been made to introduce a suitable arrival time distribution based on different interpretations and formulation of quantum theory. On one hand, according to generalized standard canonical interpretation, the arrival time distribution is considered as a generalized observable, which must be described with a positive operator value measure, or a self-adjoint operator. On the other hand, in the realistic trajectory-based formulation of quantum theory, such as Bohmian mechanics, Nelson stochastic mechanics, and many interacting board interpretation, the arrival time distribution could be obtained from particles' trajectories. In principle, the results of these approaches are different. Let's review the main approach. We begin with a standard arrival time distribution. First attempt to investigate the arrival time problem based on the standard rules of quantum theory were made at the beginning of the 16th by Avarnov and Bohm. This approach starts with a symmetric quantization of classical arrival time expression. The resulted time operator is called the Avarnov-Bohm operator. This operator satisfies the canonical commutation relation with a free Hamiltonian operator. However, it is not a self-adjoint operator, a fact that is in agreement with Pauli's theorem. The origin of this non-self-adjointness can be understood as a result of the singularity of this operator at zero momentum. As a result, the eigenstates of this operator are not orthogonal. Nevertheless, they constitute an overcomplex over complex set and provide a positive operator value measure, which are used to define the arrival time distribution. This distribution has been called a standard arrival time distribution by some others. Also, arrival time distribution has been derived in more accurate way. Here you can see some of notable papers. As I mentioned earlier, another approach to the arrival time problem is based on the Bohmian mechanics. Bohmian mechanics, also known as a pilot wave theory, is a coherent, realistic version of quantum theory which avoids the measurement problem. In Bohmian mechanics, there is no wave or wave-particle duality in usual sense. Instead, there is both the wave and particle. In contrast to the orthodox interpretation, the particle move along realistic trajectories guided by wave function, and this can provide a more intuitive picture of quantum phenomena, such as double-slit experiment, as you see. The Bohmian trajectories also can be used to give a clear prediction of arrival time distribution in a way similar to classical arrival time distribution using the trajectories. In fact, using Bohmian trajectories can be shown that the arrival time distribution is given by quantum probability current or quantum flux proposals. Let's compare these proposals in the context of double-slit experiments. We consider the joint position time distributions. Firstly, we compare the result of these proposals in the usual double-slit experiment with a vertical screen and then with a horizontal screen. As you can observe, arrival time distribution for different distance of the screen is plotted, and proposed methods are very close and not distinguishable. All results are very close. But when the screen is positioned horizontally, a notable difference emerges, especially in the near field regime. You can see how the semi-classical proposal denoted with the blue curve separated from the others. In this figure, also we can see the deviation of the standard arrival time distribution from quantum flux or Bohmian distribution, which is depicted by black curve. To have a more comprehensive insight, we can look at the joint position time distributions. These density plots clearly visualize differences between the mentioned proposals, as we can see in the insets. We can see separated fringes with different shapes. According to Bohmian point of view, there are several possible schemes to detect the particle, especially for the horizontal screen surface. because we have curved motion in y direction. The detector acts as a solid barrier. Then the first encounter with a screen will be registered as a detection. If the detector is not a solid barrier, like a point detector, we can detect the particle in the next encounters, second and third and so on. This figure shows our result which is generated from numerical simulations of the Bohmian trajectories. The background scatter plot is the position and time of arrivals, which is generated from Bohmian trajectories. The first arrival is represented by black, while the blue and green points shows the second and third arrivals respectively. The three middle graphs, middle curves, are local average arrival time. Average arrival time. The red solid line represents the quantum flux. The black solid line with empty circle marker shows the first arrival schemes, and the yellow solid line with fill circle shows the all arrivals. For more detailed conversion, we plot the arrival time distribution at a specific point of the screen, which is determined by this vertical dashed line. The result of Bohmian first arrival and all arrivals shows by black and yellow curve, while absolute value of quantum flux is shown by red. As expected, Bohmian arrival distribution is consistent with quantum flux results. However, the presence of a barrier-like screen, we must consider just first arrivals, which leads to a big temporal gap in the local arrival time distribution. This gap can be used to testing this result experimentally. Principle, the presence of the detector could modify the wave function evolution before the particle detection, even before the particle detection, which is called detector batch effect. The arrival time distribution computed so far should be considered as an ideal or intrinsic distribution, since that effect is ignored. To have a more complete investigation of detection statistics, we should consider this effect. However, due to the measurement problem and quantum Zeno effect, a complete investigation of the detector effect is problematic and at the fundamental level. And it is less obvious how to model a perfect detector. Nonetheless, some phenomenological non-equivalent models are proposed, such as the generalized Feynman path integral approach in the presence of absorbing boundary and Schrödinger equation with complex Rubin boundary condition, and so on. Resulting joint position time distribution of the three methods mentioned are depicted here. Top panel shows Bohmian first arrival distribution, middle back effect. In the middle panel, the detector back effect is considered via Rubin boundary conditions. And in the bottom panel, the detector back effect is considered using path integral with absorbing boundary approach. As seen, these distributions are different in details, and in principle they can be distinguished experimentally. We saw that there is no agreed upon answer to the arrival time problem. When and where does the wave function collapse? How one can model a detector quantum theory? Even for the famous double-slit experiment. Although the differences are small, still these predictions can be experimentally verified with a proper double-slit configuration, which is realizable using present-day single-atom interferometry technology. For example, using condensate, helium atom, and so on. In truth, only one of these proposals can explain the experimental data, if any. What is the prediction of other alternative quantum theory, such as CLS models? Thank you for your time and attention. I would be happy to answer your questions.
Thank you very much. Do we have any questions? Yeah, please.
I don't know if you know, but there's several ways to understand these delayed chose experiments in other interpretations that are not modification of the formalism, but that are conceptual. So what do you think of that? Okay, for example, I can talk about coherent histories, or the transactional interpretation, or relational interpretation. I think they all have an answer to that.
I think that in the Copenhagen interpretation, there is no clear answer, but some treatment exists. In many word interpretation, also I don't know how one can treat this problem. But in the spontaneous collapse model, seems there is some proper answer. But before the experiment, I don't know what is the result. We only want to make evidence that this experiment could be realized, and the result may be important. Okay.
Thank you. Any other questions from the audience? I mean, maybe I can just ask maybe it's a bit of a boring practical question, but probably important for the experiment. Have you thought about whether, I mean, what the effect of a little bit of decoherence between the two, let's say they're atomic beams, right, that you're an atomic cloud or something, a little bit of decoherence between the two kind of, the two slits, if you like, or the two branches of the wave function, and whether that would be kind of clearly distinguishable from these small differences that you're proposing between the interpretations.
Can you ask your question one more time?
Yeah, so imagine that I have some decoherence now, so that instead of just a perfectly coherent superposition, the kind of wave packets exiting the two arms of my interferometer now lose some coherence. Would the result be distinguishable from the kind of signals that you're plotting here?
Yes, I think that this may be occur, but the decoherence may be not enough to find a final answer.
Okay, thank you. So I think maybe let's thank the speaker and move on to the next.